Okay, so if I recall, the last question we did was these, part B, right? Okay, so now we're gonna look at in part C, and what we're looking at here in this section is, what your question?
I think there's still some parts from the.
Oh, we didn't finish part B?
We didn't do E and F.
Oh, okay. All right, let's do that then. So in the case of E, titanium, the atomic number is 22. Okay, so the atomic number of titanium is 22, right? So, if I were to write out the full electron configuration for titanium, it's going to be 1s2, 2s2, 2p6, 3s2, 3p6. So that's 18, then 4s2, and then 3d2, right? Let's see. So
Yeah,
that's
but
10.
because it's plus 3,
I'm sorry?
but because it's plus 3.
All right, so because it's plus 3, that means that we have to remove these two electrons here. And we have to remove one of these here. So therefore, the final answer will be 1s2, 2s2, 2p6, 3s2, 3p6, and then 3d1. That's it, right? So that's the electronic configuration of the titanium 3 plus ion. And then lithium, well, that's easy because lithium has an atomic number of 3. And the full electron configuration of the lithium atom is 1s2, 2s1. So in the case of the lithium plus ion, we just simply remove that electron, so it becomes 1s2, and that's it. And excuse me, this is equivalent to the electronic configuration of helium, right? So this is a configuration that that is a noble gas configuration. Okay, and that's it for the B part. Okay, so any questions? Any questions? Any questions? All right. So let's clear this and scroll down, and let's move on now to the C part. So in the C part, what we'll be concerned with is the type of properties that vary as you go from one element to the next, or from one electronic structure to the next, according to the element, across a period and down the group. All right. And in the videos I discussed, firstly, if I remember correctly, how the atomic sizes vary as you go across a period and down the group. And basically, just to summarize, if you go across any period, what you'll find is that the atomic size decreases. All right. And it's also important that you understand the reason why that happens. So let's think about what happens as you go from one atom to the next across a period. As you go from, let's take period 2, starting with lithium and ending with neon. So as you go from one element to the next, two things are happening, right? You're increasing the number of protons in the nucleus, and you're also adding an electron to the same shell, right? So as a result of those two changes, what will happen is that the increased nuclear charge will have a greater pull on the surrounding electrons, right? And therefore, as a result, as you go from one element to the next, across left to right of a period, the atomic size will decrease because the increasing nuclear charge will have an increasing attraction for the surrounding electrons, pulling those electrons closer to the nucleus, and therefore the nuclear charge, the atomic size decreases. All right. Now, the opposite is going to happen as you go down any group, right? So if you take, for example, group 1, starting with hydrogen and ending up in francium at the bottom, what you'll find is that as you go down any group, the atomic size increases. And the reason why is that as you go down a group, the difference from one atom to the next is that you're adding a shell. And that shell will have electrons in it, right? The shell that is added will be further and further away from the nucleus, right? And the atomic size basically can be seen as the distance between the nucleus and the valence shell, right? So basically, as you go down the group, the valence shell will be further away from the nucleus, and therefore, as a result, the atomic size will increase. And I think in your textbook, they're going to have a bit more detail because they talk about the fact that because you have inner shell electrons, they will repel the outer shell electrons further away from the nucleus. And that also adds in terms of the explanation as to why the atomic size increases as you go down the group, right? So that's as far as atoms are concerned. Going across a period, the atomic size decreases, going, and when I say across, I mean left to right, and then going from top to bottom of any group, the atomic size increases. Now, I went into a discussion also in the videos dealing with ions, right? We looked at how ion sizes vary with respect firstly to the atomic atoms or to the atomic sizes that they're formed from, all right? And I talked about the cations first and then the anions. Cations are the positively charged ions, the anions are the negatively charged ions, right? So let's deal with the cations first, right? So to get from an atom to a cation, what do? We remove electrons, right? So how does that affect the size of the ion compared to the atom? Well, basically, when you remove an electron from the atom, what will happen is that the nuclear charge remains the same, but the number of electrons decreases, right? So as a result, the nuclear charge or the nucleus will have a greater pull on the remaining electrons, and therefore those electrons will be drawn closer to the nucleus, and therefore, as a result, the atomic size decreases. And I think there's a table, let me see if I can find it here, which kind of summarizes with some numbers. Let's go here. When you look at the relative size of the atoms compared to the cations, which are formed from those atoms. So let me go to the PowerPoint. Chapter 8. Okay, so okay. So if you compare, for example, the sodium atom to the sodium ion, right? When the sodium atom loses an electron, basically the nucleus will have a greater pull on the remaining electrons. And as a result, you see that the ionic size of the sodium ion is 99 picometers. A picometer is equal to 10 to the minus 12 meters, right? So you see clearly there's a significant decrease in the size, right? Almost the size of the ion is almost half of that of the atom itself, right? And you see a similar trend in the case of going from magnesium to magnesium 2+. In fact, the size is more than halved in the case of going from magnesium to magnesium 2+, all right? So that shows you the relative sizes of the atoms compared to their corresponding cations. Now, in the case of anions, to get from the atom to the anion, you add an electron, or more than one electron, depending. And what will happen is that you're going to have increased repulsion between the electrons just by adding an extra electron or two, and therefore the ionic, the size of the ion will increase compared to the size of the atom. All right. So the example shown here is in the case of chlorine, where the radius of the atom is 99 picometers, and the radius of the ion is 181. So it's almost double in terms of size. All right. Oh, and this is the table I was thinking of, right? So this table basically summarizes for certain elements the sizes of ions and atoms, you know, and so on. So if you look at all the cations that are formed, let's say in group 1, the size of the ion would be smaller than that of the atom from which it is formed. So you can see that clearly in the case of lithium, in the case of sodium, potassium, rubidium, cesium, barium, all these elements here, aluminum, gallium, and so on, the ionic size is smaller compared to the atom from which they're formed. And then on the other side, where you're looking at the formation of anions, the anion size is larger compared to the size of the atom from which they're formed. So that is true for the nitride compared to the nitrogen atom, or the phosphide ion compared to the phosphorus atom, and so on, right? So those are just basically some trends, and I don't think there are any exceptions I can think of to what I just described, all right? Okay, another thing I want to talk about in relation to the questions we're about to do is that we can also look at trends in terms of ions. Oh, no, before we even say that, sorry. There's a term which I talked about, I'm going to emphasize it again here. And that term is this term right here. Isoelectronic species, right? That term isoelectronic means it's referring to atoms and ions that have the same number of electrons. So if I say, for example, that chloride, the chloride ion is isoelectronic with argon, that means that they have the same number of electrons, right? Which means that they have the same electron configuration. But not only that, you can also make predictions as to which one would be larger or smaller in size. So I think I have some examples which I went through. Okay, let's look at this example right here. So basically, you're referring to the periodic table and not to the diagram that I just showed, right? And the question is asking for you to arrange the following species in the expected order of increasing radius, right? So increasing radius meaning that you're starting from the smallest to the largest, right? So the first thing I would do is I would look at the number of protons in relation to the number of electrons in each of these, right? So in the case of calcium, I'm just going to construct a little table here. So in terms of protons, calcium has 20, iron has 26, potassium has 19, sulfide has 16, and selenide has 34, all right? So those are the number of protons. Now, in terms of the electrons, you have to pay attention to the charges, right? So in the case of calcium, the atomic number is 20, so it has 20 electrons, but because of the +2 charge here, this will be 18, right? In the case of iron, +3, so 3 from 26 gives you 3. In the case of potassium, the -1, so that's 18. In the case of the sulfide, you add 2, so that's 18. And in the case of the selenide, that will be 36, right? Now, the next thing I would do is that I would seek out the isoelectronic species. In other words, the species that have the same number of electrons, which would be the calcium, the potassium, and the sulfide, right? And I would try to arrange them in order of increasing radius, right? From the smallest to the largest, right? So which one would you expect to have the smallest radius? Of the same number of electrons, the one with the greatest nuclear charge. Because remember we said that the greater nuclear charge, the greater attraction we'll have for the surrounding electrons. So I would put calcium at the beginning here as having the smallest, calcium 2+, I'm sorry, as having the smallest radius. And then the next one in line would be potassium. And then the next one in line will be sulfide, all right? So at least for those ions, you can pretty much tell straight off which is smallest, which is in the middle, and which is the largest. Now, the problem is, where does iron and selenide fits in? Well, in the case of iron, let me see, iron is there. Okay, so iron is in the same period as potassium and calcium, right? And iron has a greater nuclear charge, right? So I would put iron, because it has the greatest nuclear charge of those three, I would put iron here, right? Because again, the greater the nuclear charge, the greater pull it will have on the surrounding electrons, all right? And then now for the selenide, well, that's kind of easy because the selenide is in period below sulfide, right? It's actually right below sulfide. So therefore, that would be of a greater size. So this would be the answer right here, right? So this would be the order of the sizes. Oh, I forgot, this should be 3+. This would be the order of the sizes of the different ions in this case, based on the information provided and based on their positions in the periodic table, relatively speaking. Okay, any questions about this one? Any questions? Any questions? Any questions out there in Zoom? Also, people came in late. Let me get the attendance of those persons who just joined us. Let me see here. Davis. Or I got Davis already. McFadden, I think I got McFadden already. Yeah, I got McFadden already. Scalf. Okay, so now Scalf is here. And let me see who else. Lush is here. And Rodriguez is here. All right. Okay, so if there are no questions about this, we can now proceed to the relevant question. So let me go back to okay. So it says, given the set of ions and atoms, arrange them in order of increasing size. So again, from the smallest to the largest. So of these three, I don't know what I put here. Of these three, which you'd expect to be the smallest? Let's start off with the smallest. Fe3 plus. Then
FE2.
Fe2 plus, and then of course Fe. That's it, right? And this is primarily due to the charge, right? The fact that Fe3 plus would have less electrons. They have the same number of protons, but the number of electrons will be different. So therefore, the one with the smallest number of electrons will have a smaller size. Okay. B. S2 minus, AR, and Se2 minus. Now, in this case here, since we're dealing with different elements, I would do the same thing like I did in the previous example. I would find the number of protons in each case and the number of electrons, right? So in the case of the sulfide, the atomic number is 16. In the case of the argon, the atomic number is 18. And in the case of selenide, the atomic number is 34. And then now for the number of electrons, that would be 18 for sulfur, 18 for argon, and 36 for the selenide. Okay, so based on what we have here, which would be the smallest in terms of size?
Okay.
Argon, okay, followed by
So,
sulfide, and then selenide.
Yeah.
And that's it. All right. Any questions about this? Any questions? Okay, so for C, you're given aluminum, chloride, sulfide, and potassium. So again, I'll take the same approach. I'll find the number of protons in each case. So aluminum is atomic number 13, chlorine is 17, sulfur is 16, and potassium is 19, right? In terms of the electrons, aluminum is 13, chloride is 18, sulfide is 18, and potassium is 18, right? So the chloride, sulfide, and potassium are all isoelectronic. So which one would be the smallest in terms of radius? Potassium ion, followed by
the chloride.
chloride ion, followed by
Right.
the sulfide ion. Okay, so this begs the question, where does aluminum fall?
In the beginning.
Exactly. Aluminum would fall in the beginning because aluminum is in the earlier period, all right? Okay, any question about this one? Any questions? Any questions? No questions? All right. So let me clear this. Oh, yes, sir.
Yeah, that kind of view on how they were so. How the small stuff. Because
Okay, well, what I did first was I identified these as the isoelectronic series, right? Meaning that they have the same number of electrons, right?
Right.
And basically, once you identify that, the one that is smallest is the one with the greatest nuclear charge, right? So if you have three structures with the same number of electrons, right? You look at first which one has the greatest nuclear charge. That one will be the smallest. So that's why I put potassium here first, right? And then the next would be the chloride, because its nuclear charge is 17. And then the one with the greatest radius would be sulfide, which is 16. So once I've established these three, I now need to figure out where aluminum comes in, because aluminum is given here. And because aluminum is in period 3, all these other structures that we just discussed, well, actually aluminum is to the left of the chloride and and all the others, all right? So therefore, I would expect that, hold on, wait a minute, did I misspoke? Chloride, sulfide, potassium. Actually, aluminum should be here, actually, my bad. Because the atomic size decreases as you go from left to right. I didn't read the periodic table correctly. I mistakenly put the aluminum in the higher period. They're in the same period as sulfur and chlorine. Right?
But
So,
it's before, it's above K. Yeah. it's above X. And 1313 is gonna be a lot stronger than the other numbers.
the thing is that aluminum, if you just look at the atomic structure without any ions or anything like that, right? Aluminum will be larger than sulfur and the chloride.
But it would be smaller than potassium,
Hmm?
but it would be smaller than potassium. Cause it's on a level above.
That's true too. Interesting. It would be smaller compared to potassium,
In your chlorine.
compared to the potassium atom, but the potassium ion is smaller than the potassium atom. You see what I'm saying? So that's why I'm thinking that aluminum should be here. I'll check and make sure, but now that I'm thinking about it, let me make a correction here. So I'm saying that the aluminum would be here, but I'm going to go back and check and see.
You don't think though that with aluminum being 1313, that would be a evenly stronger pool?
You know what? I think I can check something now, actually. Hold on. Let me go to the PowerPoint and then we'll just. Let me clear this. Okay, so this. Okay, let's see here. Aluminum is here. So actually aluminum is smaller. Because aluminum is here, aluminum 3 plus is 50. Sulfide is 184, 181. Yeah, so
But it's not the ion. It's regular.
no, the aluminum ion is here.
Yeah, but on our paper, it's regular.
Oh, it's regular aluminum? Oh. I guess that's where I'm messing up. Oh, it's regular, okay. So
Everything else is not.
well, it's still smaller. The way they have it is that aluminum is smaller than this, smaller than that.
But it's
So
bigger than the potassium.
but it's bigger than the potassium. Yeah, that's it's kind of hard. It's kind of unfair to ask you this question. But I'll check and make sure. So it seems as if based on this information here, that the aluminum would be
Between potassium.
between the potassium and the
Chloride.
and the chloride, yeah. Yeah, that would be an unfair question to ask you guys. I promise you I won't give you a question. Okay, so the actual answer is. What did I say now?
A plus,
A plus less than Cl minus,
no, AL.
less than Al. Less than Cl minus.
Yeah.
And then less than sulfur. Okay, so that's the actual answer,
That
all
one
right?
definitely tricked me.
What's that?
So that one definitely tricked me.
Yeah. I think it would be unfair to ask you guys, a question like this. based on just trends. Okay, so let me clear this. And scroll down. Oh, here's another one. Okay, so let's look at this one here. Hopefully this one is not as tricky. Okay, so again, I would try to identify the isoelectronic series. Protons, sulfur is 16, chlorine is 17, potassium is 19, calcium is 20. And then in terms of electrons, this will be 18. This will be 18. This will be 18. They're all 18, right? So this one is easiest to deal with because they're all isoelectronic. So which one would you place first as the smallest one? Calcium, followed by K plus, followed by Cl minus, and then sulfide. Yeah, so this one is easier to deal with. All right, very good. Let me clear this and scroll down. Okay, so now we're going to get into some other trends in terms of physical properties of atoms, elements, and periodic table. So the first question is being asked here, what is or define ionization energy, right? And let me just give it to you right here. Basically, it's the energy required to remove an electron from a gaseous atom. So it's the energy required to remove an electron from a gaseous atom. So if you have an atom X, right, and you wanted to convert it to X plus, you have to remove an electron, right? The enthalpy change for that would be the ionization energy. All right. Please note the definition. Didn't complete that sentence. Please note that one important aspect of the definition is right here. The atom has to be gaseous, right? So you're starting from a gaseous atom to the gaseous ion, right? The energy required to make that change is the ionization energy, right? And let me just say this, and I think I went through this in the videos as well, right? You can have what is called the first, second, third ionization energy, fourth, and so on, corresponding to the removal of electrons each time, right? So if you take an element like boron has 5 electrons, right? So a certain amount of energy is required to remove the first electron, and then another amount of energy is needed to remove the second electron, and so on and so forth, right? So in the case of boron, there's a total of 5 ionization energies associated with that. Another thing I need to say also is that what you'll find is that the amount of energy that is needed to remove subsequent electrons increases, right? So a certain amount of energy is needed to remove the first one, and then more energy is needed to remove the second one, and so on and so forth. And the reason for that, again, has to do with the fact that when you remove the first electron, basically what you're left with is a positively charged species, right? So to remove another electron, it's going to be more difficult because you're going to remove something that is negative from something that is positively charged, right? And that increases the charge in each step, which means that it becomes progressively more difficult to remove electrons, and therefore the ionization energy will increase with each step. Okay, so that's question number 1. Question number 2 says, what trend in the ionization energy do you see as you go down a group on the periodic table? So we're talking about going down any group, right? Now, remember what I said earlier with respect to atomic size. As you go down any group, the atomic size increases, right? Which means that the distance between the nucleus and the valence electron increases. So my question to you is, what do you think would be the trend in terms of the ionization energy? Remembering that the ionization energy is the energy needed to remove that valence electron.
So if it's only your first energy,
Mhm.
it would be decreasing.
Exactly, it's going to decrease as you go down the group. Because as you go down the group, the distance between the nucleus and the valence electron will increase. That means that the hold or the attraction between the nucleus and that electron will decrease. So therefore, it's easier to remove the valence electron. So therefore, if you take, for example, group 1, hydrogen will have the highest first ionization energy, followed by lithium, followed by sodium, and so on. So to answer number 2, it decreases. All right. And then to explain where it says what caused the trend, as we go down the group or any group, let me put any group. Any group, the distance between the valence electrons and the nucleus decreases. Increases, I'm sorry. Therefore, the attraction between those electrons and the nucleus decreases. Making them easier to remove. Easier to remove. And that's it. So that's why you explain that trend. As you go down any group, the distance between the valence electrons and the nucleus increases. The attractive force between the nucleus and those electrons will decrease, and therefore it's easier to pluck those electrons from the valence shell, and therefore less energy is needed. All right? Okay, any questions about this? Any questions about this? Any questions? Okay, let me clear this. And scroll down to question number 4. So question number 4 is asking, what trend in ionization energy do you see as you go across a period or row in the periodic table? So again, going back to our discussion about how the atomic size varies as you go from left to right. Remember we said as you go from left to right of any period, the atomic size decreases because you're adding a proton to the nucleus, you're adding an electron to the same shell, so therefore increasingly as you go from one element to the next of any period, there's a greater attraction for the surrounding electrons, and therefore the atomic size will decrease. So what effect would that have, based on what I just said, what effect would that have on the ionization energy as you go from left to right? I'm sorry?
Increases.
Increases, exactly. So increases. Okay, so let me hear your explanation for that now. Anybody, not just you, anybody. So remember what I said in terms of explaining the previous trend. So what would you write down here? What caused this trend? Let me start here. As we go from one element to the next, what happens? As you go from one element to the next, what happens?
The pull of the protons in the nucleus get stronger.
Okay, so
Making the
increasing the pull of the nucleus on the surrounding electrons becomes stronger, which is true. On the surrounding electrons become stronger.
requiring more energy to remove the valence electron.
Okay, requiring more energy. Requiring more energy. Energy to remove the valence electron. Exactly. I would give full credit for an answer like this. The valence electrons. Okay, and that's it. All right. Going from left to right, the nuclear charge increases, pulling the electrons closer to the nucleus. So therefore, more energy is needed as you go from left to right to remove that valence electron. All right. Now, there are some exceptions to this particular trend, right? Let me put here in parentheses, some exceptions. I won't go into it right now, but I'm quite sure I discussed it in the video, so you may want to rewatch those videos if you want to see the exceptions. If I remember correctly, the exception has to do with going from nitrogen to oxygen and from beryllium to boron, right? There's a slight decrease in ionization energy as you go from beryllium to boron and as you go from nitrogen to oxygen. But I'm gonna leave you guys to watch the videos or read the textbook. And if you have any questions about that, then you can contact me and I'm more than willing to discuss that. Okay. Number 6, it says circle the atom in each pair that has a greater first ionization energy. All right. So basically, you're going to be looking at the 2 elements in each pair, and you're going to decide which one will have the greater first ionization energy. And the first pair is lithium and beryllium. So between those 2, which would you expect to have the higher or greater first ionization energy? Hmm?
B.
Beryllium, exactly. So beryllium would be the answer for A. What about B? Between sodium and potassium, which would you expect to have the first, I keep saying first, the highest first ionization energy?
Sodium.
Exactly. Because remember the first ionization energy decreases as you go down the group. So sodium is above potassium, so therefore sodium would have a greater first ionization energy. Okay, the next one is chlorine and silicon. Between chlorine and silicon, which would you expect to have the greatest first ionization energy? Between chlorine and silicon. Okay, so where's chlorine? Chlorine is there.
Oh, would it be chlorine?
I'm sorry?
Or would it be chlorine?
Yes, that's what the chlorine. Because silicon is to the left of chlorine in the same period, right? So therefore, chlorine would be the answer in the case of C. Okay, calcium and barium. Calcium and barium. Which of these 2 would you expect to have the highest first ionization energy? Calcium, I would agree with that. Okay, very good. E, phosphorus and argon. Okay, where are they? Phosphorus is there. Argon is to his right. So which would you expect to have the highest first ionization energy? Argon would be correct. And then the last one, F, lithium and potassium. Of those 2, which would have the greatest first ionization energy? Lithium would be correct. Okay, very good. Alrighty. Any questions about these? Any questions? Any questions? Any questions out there in Zoom? You guys out there in Zoom, please feel free to chime in. Let me clear this. And let's move on to number 7. Okay, now in this case, it's asking for you to, okay, so they give you a set of atoms, and you're going to order them in terms of lowest to highest first ionization energy. Okay, so let's start off with A, 7A. Of these 3, okay, let's see where their positions are. You have magnesium over there, you have silicon in the same period in the middle, and you have sulfur more to the right. Okay, so which would be the one with the greatest first ionization energy in this series?
Well, I have them in order, right? It's lowest to highest.
Oh, no, it said, oh, lowest to highest, I'm sorry. Oh, yes, it's actually in the correct order as it is. So magnesium would be the lowest, followed by silicon, followed by sulfur. Okay, very good. B, magnesium, calcium, and barium. So of these 3, which would be the lowest? Let's start off with the lowest between those 3. Magnesium, calcium, and barium.
It'd be barium.
Barium first,
calcium,
and then calcium, and then magnesium. Okay, good. C, fluorine, chlorine, and bromine. Of these 3, which would have the first? The highest, I should say. I'm sorry, the lowest. First ionization energy.
Bromine.
Bromine, then chlorine, then fluorine. Very good. Okay, the next one, B, barium, copper, and neon. Okay, so this one is more tricky. Where's barium? Barium is down here. And then copper is more to the right and up. And then neon is even more to the right and up. Okay, so which of these do you expect to have the lowest? Barium will be the lowest, so BA first, followed by
Copper.
copper, followed by neon. So it's in the same order as given in the question, so that's that. Okay. Any question about these? Any questions? Any questions? Oh, here's one more. Okay, I didn't see that one. Let me clear this. Okay, so this one, they gave you silicon, phosphorus, and helium. Okay, so silicon is there, phosphorus is right to the immediate right, and helium is to the right and above.
It's like it's already.
Yeah, it's in the correct order as well, so the answer will be silicon first, followed by phosphorus, followed by helium. Okay. All right, so that's it. Okay, so that's assignment 8. Let me set up a Dropbox for this. So let me go here, let me go here. Let me go assignments.
Can I ask a question?
Yes, ma'am.
So if in that case, you only have one noble gas, will the noble gas always be the highest ionization energy? If you only have one?
Right, yeah. Yeah. Well, it depends actually, hold on. Because let's say.
Cause wouldn't it be harder, cause they're so in equilibrium to pull a valence?
I think you're right. I'll have to think about that some more, but just my immediate reaction would be you're correct. So yes, I would say you're correct. But if I think about it some more, then I can probably come up with an example where that's not the case, then I'll let you know.
There's probably always exceptions.
Yeah. Okay, so today is the 31st of March, 2026. So I'm going to let the assignment be due on Thursday. So let me go here.
You know how to do that easier?
Hmm?
Know how to do that easier?
Oh,
Hit clear first. That will clear to the right, and then it'll start you on today's date.
all right. Oh, shoot, thank you. Oh, hold on, I made a mistake. This will be, hold on, not date. Cannot be before the due date. How did that happen?
Oh, the time.
Oh,
Scroll all the way down.
sure, oh,
Change the 3059. Don't know why it's not. Very strange.
oh, okay. All right, so in the time that we have left, what I'm gonna do is I'm gonna start off with a discussion of chapter 9. Before I forget, let me pause the videos for chapter 9. But I'll start you off, and then you can watch the rest of the videos for chapter 9. Chapter 9 deals with a very important topic. What's going on? Let me publish this. Okay, so the videos for chapter 9 is now available. So I'm going to start you off. So let me just go to the PowerPoint for chapter 9. All right, so chapter 9, oops, what did I do? Okay, so chapter 9 is dealing with the important concept of bonding. And this is important because you need to understand that when it comes to compounds, one of the reasons why compounds are stable under normal conditions is because of attractive forces that exist between particles. Hold on, give me a minute here. Let me publish this for you guys out there in Zoom. That's the PowerPoint for chapter 1. All right. So, whenever you hear this term bond, it's basically an attractive force, right? So these are the forces responsible for holding atoms and ions together so that they, become stable. Where's the state? Okay. And the basic nature of these forces is that they're electrostatic, which means that these are attractive forces between particles of opposite charges, right? As we all know, opposite charges attract and like charges repel, all right? So just to illustrate, using a very simplistic model, and this is very simplistic in terms of the hydrogen molecule, right? So in the hydrogen molecule, you have two atoms of hydrogen. Each atom will have a proton and electron, right? So one can envisage a situation where if you have these two particles close to each other, the electrons will be repelling each other and the protons will be repelling each other, right? But you can also have attractive forces between, let's say, this proton and this electron and this proton and this electron, and finally this electron and this proton, right? So basically, for the structure to be stable, you need to have a balance between these charges such that basically the total amount of attractive forces will be greater than that of the repulsive forces. And therefore, as a result, the resulting structure will remain stable, all right? And as stated here in this green color right here, one of the factors that affects the stability is how close these particles are to each other, especially with respect to the distance between the nuclei, all right? So talking about the hydrogen atom, we have this diagram right here, which shows you basically the changes in energy as you change the distance between the two nuclei in the molecule of hydrogen, right? And one model that is used that can be helpful in terms of understanding this, you can imagine a hydrogen molecule being similar to two balls, let's say two steel balls connected by a spring, right? So the balls will represent the atoms and the spring will represent the bond, right? So we all know what would happen if you were to force the balls close to each other, right? There'll be a resistance, right? And therefore, what that basically means is that there will be an increase in energy associated with that. And that is what is seen here. Now, here is where the hydrogen molecule is more stable. If you bring the nuclei closer to each other, in other words, you reduce the internuclear distance, the energy increases, as you can see on this part of the graph right here, all right? On the other hand, if you want to pull the atoms from each other, there's also going to be a corresponding energy increase, but you're going to get to a point where the bond is broken, right? And therefore, basically, the energy of the molecule will be effectively zero, in reference to the axis that is shown here, all right? So there is a minimum point, energy-wise, represented right here, which is minus 436 kilojoules per mole. I mean, this is something that has been experimentally done. And that represents the most stable arrangement. And at that point, the distance between the two nuclei would be 74 picometers as indicated here, all right? So that's basically how the changes in energy would occur as you change the internuclear distance between the two hydrogen atoms. And that is true for pretty much all covalent bonds. You have that similar effect. Okay, so let's talk about the Lewis theory of chemical bonding. So this is a theory that is put forward by a guy by the name of G.N. Lewis. He has made some significant contribution to our understanding of bonding and of ions and so on, right? So most of what we have learned in regards to those topics, he is a key player in terms of coming up with discoveries which basically deepen our understanding. when it comes to these topics, right? Now, according to his theory, the valence electrons are the electrons that play a fundamental role in chemical bonding, right? So if you look at the formation of compounds between metals and nonmetals, what happens is that you would have the transfer of valence electrons from the metals to the nonmetals. And therefore, as a result, you would have the formation of ions, and those ions will be oppositely charged, and therefore, because they're oppositely charged, they'll be attracted to each other, and they form what is called an ionic bond. So the attractive force that exists between ions of opposite charges, we call that ionic bonds. But you also have another possibility where you have two nonmetals coming together, and instead of having the transfer of electrons from one to the other, you have the sharing of electrons between those two atoms, right? So basically, as a result of the sharing of those two electrons or pairs of electrons between the two atoms, you're going to have an attraction between the separate nuclei and the shared electrons, and that attractive force is called the covalent bond. All right. So basically, that's what happens when bonds are formed. And what you'll find is that in the formation of these bonds, where you have losing, gaining, or sharing electrons, these atoms tend to, not always, but they tend to end up with a full octet of electrons in their valence shell. In other words, they will acquire the same electronic configuration as their nearest noble gases. But this is not true in all cases, as you're going to see shortly. All right. So this brings us now to this whole concept of Lewis symbols, right? It's a very simple concept. It's very useful when it comes to explaining and showing what we just discussed in terms of the formation of covalent and ionic bond, right? So basically, it's very simple. The Lewis symbol is basically the symbol of the element, and then you put dots to represent the electrons in the valence shell, right? So it says here in writing Lewis symbols, the first four dots are placed singly on each of the four sides of the symbol, and then the dots are paired as the next four are added. And we see some examples right here. So for example, the Lewis symbol for lithium is simply the symbol of lithium with a dot, that's one electron, and then you have the symbol for beryllium, boron, carbon, and so on. As you can see, you add a dot. You space them out first before pairing them, all right? Okay. So if you're asked for the Lewis symbol of magnesium, the silicon, and phosphorus, well, that's very simple. Magnesium is this. Silicon is
It's just valence.
just the valence electrons, exactly. Just the valence electrons. And then the phosphorus, which is in group 5, is, that's it, all right? So that's basically how you draw the Lewis symbols for elements. Later on, we're going to learn about drawing the Lewis structures for molecules and polyatomic ions. So that's slightly more complicated than what we just did here, but that's for later on, all right? Okay, so that's Lewis symbols. Now let's talk about ionic bonds first, and then we're going to talk about covalent bonds in more detail, right? So as we said before, ionic bonds are formed when you have atoms. But firstly, ionic bonds are typically formed between metals and non-metals, right? And what will happen is that, as I said before, the metals will lose electrons, and those electrons will be transferred to the non-metal, right? Now, as a result, they may acquire noble gas configuration, but please remember that they're not becoming noble gases, right? So basically, as stated here, the ions are formed in a reaction between a metal and a non-metal, and they will have opposite charges, and then therefore they'll be attracted to each other strongly, and they will form what is called an ion pair, right? And therefore the attractive force that exists between these ions is called the ionic bond. And the result of that attraction is that at a gross structure level, you're going to end up with a highly ordered array of the ions, and that is called an ionic crystal, all right? And I think I have some diagrams here. So here's an example. The reaction between sodium metal and chlorine is a very explosive exothermic reaction. So the flask contains chlorine, right? And if you drop a small amount of sodium, boom, you get a big exothermic reaction, produces a lot of heat and light, right? And then when things cool down, you're going to end up with crystals of sodium chloride present. So you're going to see some crystals looking like this. And the reaction that is taking place here is where the sodium atoms transfers electrons to the chlorine atoms, and you end up with the sodium chloride product. Now, what you'll find is, as I said before, the arrangement of the sodium and chloride ions throughout the structure will be a very highly ordered arrangement, as you can see here. So this is basically the arrangement of the sodium chloride compound. And this is also a small picture of the same thing. Again, you see it's a highly ordered arrangement. And this is true for pretty much all ionic compounds, right? What you'll find is that the arrangements will be different depending on the different compounds, and it's largely dependent on the relative sizes of their anions and cations. But basically, they all have the same feature where you have the formation of an ordered array of ions to form an ionic crystal, all right? So this is so that's that as far as sodium chloride is concerned. Okay, now we can use the Lewis symbols to represent the type of bonding that takes place between a non-metal and a metal. The example that is shown here is the example of the formation of sodium chloride. So this is the sodium atom, this is the chlorine atom, right? The electron here will be transferred from the sodium to the chlorine. So the sodium now ends up with a plus charge and the chloride ends up with a negative charge. And that's basically how we use the Lewis symbols to represent how an ionic compound is formed, in this case, formed from sodium and chlorine. So we can apply this to the formation of this idea, this concept, to the formation of pretty much any ionic compound that is formed from a metal and a non-metal. So you could do the same thing for magnesium reacting with oxygen to form magnesium oxide, or calcium reacting with chlorine to form calcium chloride, and so on and so forth. Okay, so in fact, let's look at this example right here. It says, use, what time is it, by the way?
49.
Okay. So this question says, use Lewis symbols to show the formation of ionic bonds between the magnesium and nitrogen. What are the name of the formula? What are the name and the formula of the compound that results? So magnesium, the Lewis symbol for magnesium is that, and the Lewis symbol for nitrogen is this, all right? Now, you can start off by transferring electrons from here to here and from here to here, right? But basically that won't be enough because nitrogen needs to have 8 electrons. So you're going to need another magnesium atom. Oops, sorry. You're going to need another magnesium atom. And one of these electrons will be transferred to this nitrogen atom. But here now we have an extra magnesium, so we need another nitrogen atom where this electron can be transferred to. But now we have this nitrogen here, which apart from getting this electron here, it's going to need 2 more electrons. So we're going to need another magnesium here to contribute 2 electrons. So 1 electron will go here, and the other electron will go here. So you're going to end up with 3 magnesium ions and 3 nitride ions. And that's basically the Lewis symbol. Oh, wait a minute, I made a mistake. It should be 2, not 3. Okay. So that's basically the Lewis symbol representation. The question is asking for the name and the formula, where the name of the compound would be magnesium nitride. And the formula would be Mg3 and 2. And that's it. All right. Okay, any questions about this? Any questions? All right, so let me clear this. Continue. Okay. Ooh. Don't want to talk about this now. All right. Let me go ahead. So what we're going to look at here in this section is a discussion of how the energy changes that will take place as you go from the metal reacting with the non-metal to the final product, which would be the ionic compound, right? Now, what you're looking at here are data for the first ionization energy of sodium, which we talked about earlier, right? Which is, in this case, 496 kilojoules per mole. And this here represents the energy change when chlorine gains an electron to form a chloride ion. That is called the electron affinity, right? Now, as stated here, from the data that is given above, it does not appear that the formation of sodium chloride will be energetically favored. And the reason why that is so is because if you were to add these two together, you're going to get a positive value for the enthalpy change overall. And that is usually not favored naturally, all right? Okay, so we're going to talk about what is called the enthalpy of formation, which is actually more important than either the first or second, the first ionization energy or the electron affinity, all right? So in order for us to look at this in more detail, we're going to be using what is called a Born-Haber cycle. The Born-Haber cycle basically is a diagram which shows you the changes that the different species will undergo as you go from the separate elements, the metal and non-metal, to the final product, which would be the ionic compound, right? So this is the Born-Haber cycle for sodium chloride. I'm going to explain each step, right? So basically, we're starting from here and we're going to end up here, right? Now we can go from here to here directly, and that has been done. People have calculated the enthalpy change going from here to here, and that is called the enthalpy of formation, right? That is, of course, the enthalpy change that takes place when you start off with the elements and you end up with your product, which is sodium chloride, right? And that was determined to be equal to minus 411 kilojoules, right? Now, what we're going to look at is the other changes that will take place as you go from sodium and chlorine all the way around here to the final product, right? And basically what you're going to do is, well, based on Hess's law, we will see that the sum of all these energy changes here will be equal to the energy change as they go from here to here, right? So we're going to start with step one right here, right? Step one, which involves the conversion of sodium solid to sodium gas. Sodium solid to sodium gas. Now, I don't know if I've introduced this term to you before, sublimation. Sublimation basically means that you're going from solid to gas directly without going through the liquid state, all right? Do you all know what dry ice is? Right, dry ice is frozen carbon dioxide. And if I take a piece of dry ice and put it on this bench right here, and just leave it, you're going to see some fumes emanating from it, right? Basically, the solid carbon dioxide is converted to gaseous carbon dioxide without going through the liquid state. So therefore, if I put a piece of dry ice here and leave it, eventually it's going to shrink, and basically disappear. You won't see any liquid left on the table, right? And that's because it goes directly to the gaseous state. So it's the same thing that we're talking about here. We're going from the solid state of sodium to the gaseous state, right? And that's sublimation. Excuse me. And the enthalpy that is used here, or the energy that is required to make that transition, that is called enthalpy of sublimation. Enthalpy of sublimation, right? So that's the first step, going from sodium solid to sodium gas. And then now, to go from chlorine molecule to chlorine atoms, that is called atomization, right? So this enthalpy here is called the enthalpy. Oh, another term that is used, which I think I'm going to stick to, actually, is bond dissociation energy. Bond dissociation energy. It's the same thing as atomization, but I think in most textbooks they use bond dissociation energy, also known as BDE. All right? Okay, so at this stage, we have a sodium gas and chlorine gaseous atoms. So now what will happen next is you're going to have the energy, I'm sorry, not energy, you're going to have an electron being removed from the sodium gaseous atom to the sodium gaseous ion, right? And we just met that term earlier, that is known as ionization energy, right? So this here would be the first ionization energy. Ionization energy of sodium, all right, which is 496 kilojoules, right? So that's why you see this electron here, because the sodium atom loses an electron to form the sodium ion, and you have the electron being produced here. The next step is where this electron combines with chlorine to form the chloride ion, and this is called the electron affinity, all right? So the electron affinity of the chlorine atom is minus 349 kilojoules, right? And then finally, to get from here to here, now here's where there's a bit of confusion depending on the textbook that you're using, right? So let me explain what's happening here. What's happening here is that the sodium will combine with the chloride to form sodium chloride, and this energy here is the amount of energy that the energy change that will take place when these two ions come together to form the sodium chloride. And this is called the lattice energy. Now here's where the confusion comes in. In some textbooks, they define the lattice energy as the energy where the ions come together to form the solid, right? In other textbooks, they define it as the other way around, where the solid become the ion, right? And if I'm not mistaken, your textbook describes it that way, right? So I'm going to stick to that definition when it comes to the textbook, because you're using a textbook which has that definition. So the lattice energy would be the energy where you have the sodium chloride forming the sodium and chloride ions, right? Which means that according to that definition, this would not be negative. It would be positive 787 kilojoules, all right? So we're going to stick to that definition. The lattice energy for any ionic compound is the energy that is needed to break up the ionic compound to form the gaseous ions, right? So that's the definition we're going to stick to, okay? So with that in mind, we can calculate the lattice energy, which is usually what you're asked in most of these problems. And the main reason why is because the lattice energy is seen as a measure of the stability of the compound, right? The greater the stability of the compound, the greater the lattice energy is, all right? So basically, I'm going to show you how to, I wish I had space here. Let's see. Okay, hold on. Okay. All right, I'm going to see if I can squeeze it in here. In this corner here. Okay, so I'm going to show you the relationship between these terms, right? So according to the Born-Haber cycle. So I'm going to start here, right? So delta H1 plus delta H2, right? So that's 1, 2, and then plus delta H3, right? And then we go over here, plus delta H4, right? And then plus delta H5, right? And all of that added together would be equal to delta HF, right? So going from here, and in all these values all around here, right? That would be equal to going from here directly to here, right? So if you put all these numbers into this equation here, you'll see that all these added up will be equal to minus 411 kilojoules. All right? So that's basically how the Born-Haber cycle works. And I think the next slide is
If we follow our book's definition of lattice energy and it becomes positive, the case is not that it's negative 411, then.
I'm sorry?
Then it would change the final.
No, because okay, let me I understand what you're asking. It's not, you mean this here would change? No, it won't.
If you change that to positive.
But remember, we're talking about going in that direction.
Oh, so we're doing the opposite of. what-
Exactly, because the definition in your textbook is opposite to what I have here. In
So
terms
we're
of. the-
doing the opposite. lattice.
Exactly,
Okay,
exactly.
I understand.
All right, okay, I don't think I have time to go into the actual example, which I think is on the next page. Let me just check something here. Okay, so this is an example. When you watch the video, you'll see that I've gone through this example right here. So, make sure you watch the videos and, for the rest of the chapter. If you have any questions while watching the videos, please feel free to come and see me. Let me remind you also that your test is in the testing center. Make sure that, make sure that you demand, don't demand, that might be a bit. That probably won't be, appreciated. But let them know that, you should get your tables. Again, last time I had some issue with students not getting their tables. I forgot the number of pages, but I think I told you guys the number of pages, right? That I did?
No.
Oh, sure, okay. I need to do that today.
I think it was like 7. With the first page.
Including the cover page. Let me check here. Hold on. Let me check. Okay, so let me go to announcements.
Maybe that was just for the first test.
I thought I did that for this test. Okay, I thought okay, I need to send you that information. I don't remember the number of pages right now, so. I'm gonna do that when I'm eating lunch. But whatever number of pages, make sure that you count it and let them know, this is what I said that you guys should get. Hopefully you won't have any issues. All right. So that's it, folks. I'll see you guys next week.
Professor,
Yes,
I'm
ma'am.
still missing my testimony safety. Right.
What's the last name?
That good.
Oh, let's see. Whatever great for you here.
It's not in here, this.
Put it in.
Yeah.
Did I send it back to you?
No, sir.
Okay, I have to. Let me see. Meantime. Okay, let me let me go here. I mean, not the second, that's. One. Okay, I'll have to do it for you. But I do have a grade for you here.
Okay.
But normally I think I save it on this thumb drive, but I don't see it here, so let me look for it and send it to you ASAP.
But yeah, I have the same thing. My test one isn't
What's your last name?
Candace Brown.
Okay, I definitely don't have a study. Okay, so I have to set for that one as well. All right.
You look at something for me, what is that?
Oh, okay.
So my nomenclature says escape, but you returned it.
Okay, oh. Oh, yellow color. And this is, And which one is this?
No,
Looks like I did that for everyone in your group. Have to ask them to,
bring it back.
yeah. Okay, so, we'll go here. Wait a minute. I only have one. Okay, I need to make an announcement here, perhaps. Because I have one person submitted online, but I thought I collected. I really don't want them in person. Anyway, I'm going to make an announcement about it.
Tell them to bring it all back.
What's that?
Tell them to bring it back.
Yeah, because,
I think it was in your other file. You probably just got passing out.
it happens.
They have to have too many papers.
And I challenge to keep trying. I try different methods and. Oh. You used to teach, right?
Yeah, I teach nursing though.
What's that?
They're just nursing.
Oh, nursing? Just nursing, that's important. Oh.
I teach pharmacology and
So what kind of students you teach, like LPN?
RN. I do RNs and I do bachelors.
Oh, really? Oh, okay. Cool. So where you used to teach at?
I teach at Taylor College
Oh, okay.
and then I also teach on an online program for the bachelor.
Oh, okay. Oh, which one? I keep getting these nursing stories. You probably heard of this one. The hospital in Ocala is suing Rasmussen College. Is all I want.
There's so many crazy things. There was like a whole scandal.
Yeah,
About, I think,
apparently it was a male nurse and apparently he wasn't prepared. They were lifting an 8-year-old patient.
yeah,
And
like,
the patient fell and died.
and he wasn't assigned to that area at all, so he must have been walking by. But then it's like, was he walking by and she was already getting out of bed and he was trying to
Right.
corral her back in? I don't know. But like 5 years ago, they caught like a whole school in South Florida just selling degrees.
Oh, Lord.
Right?
Oh, no, you're fine, you're fine.
And like that was the whole thing, so like a bunch of people got their degree because they bought it.
Well, I'm scared to be a patient in the hospital in Florida
It's
right now.
very scary. It's very scary.
I'll be like, okay.
That school even thought that was okay. To do.
And you know, that's what, there's another lady, she was saying, she was talking about another scandal. This thing one I was telling you about where, this
The
person was
testing?
the testing one, right? And the person was making a commentary about that, was that, because in that story, it was a dean who was a proctor, right? Which was unusual, because usually it's a ordinary faculty member that they use. And the person was commentating, they were saying that, you know, it was good on the dean for her to do that, because she said, the person who was commentating, because she's a nurse. She said that she knew personally of other situations where the administration just don't care, you know,
No, they just sit there.
they just look this way while the cheating is taking place and all that.
That's something really cool, like a school
Mm.
in Taylor, like they have cameras. And you can see everyone's computer on the camera,
Oh, okay.
and then the cameras also have microphones.
Oh, okay.
And then they have, of course, they have to sign an agreement before school, like letting them know you're
Right.
being recorded.
Yeah,
So like if you suspect anything, you can just pull up the video.
exactly.
But it's sad that you have to do that.
Oh, yeah.
Very sad. Well, I'll see you later.
Yes, ma'am. Okay. So let me go here. Oh, here you go.
Oh, thank you.
For today.
How
was Chipotle?
It was good. Yeah, usually, I like your food.
Me too, me too.
You're not bad at all.